Hello, everybody. We are Team 12, Mecha-Megolodon. This is our Gate 5.5 presentation. My name is Trenton Praski.
I'm Keenan McKibben. I'm Gregory.
I'm Shae Rittenberry.
I'm Jason Jong.
Let's start off and get into some problem and scope of work. So just to start off with the problem description, the main thing would be the main goal is to just fabricate a life-size 9-foot shark. And also to create the shark with naturally swimming motion using the tail to generate thrust with pneumatics controlled by a proportion air MPV pressure regulator manifold. The main thing would be using those proportion air products like that manifold to get this shark propelling into the water with the pneumatic power. And also controlling the shark with wire controls and tethered air. Off to the right, you can see also a diagram of Bevan the bull shark. This is actually important for us to include because it's actually the model from our shark. It's actually modeled off of a real life-size shark from Australia. Next, onto the scope of work. We have these 6 bullet points over here: result, functionality, realism, resources, safety, and learning. Obviously, the result would be the life-size pneumatic shark. And functionality and realism kind of go together. There's a preference for realism, but functionality kind of takes priority over size, making sure all the systems are right and working well. Also safety, working with the high pressured air and not making sure the teeth aren't too sharp. And lastly, just that learning phase of making sure everybody's understanding the electro-pneumatic systems of the project.
We wanted to make sure to have some methodology during this project. We followed the 5 steps of empathize, define, ideate, prototype, and test. A lot for this 5.5 demonstration is the ideate, prototype, and testing. We had a 3D model this semester that we created in SolidWorks, and then we got to prototype it, actually manufacturing the shark using a lot of laser cutting and using other tools in the shop, as well as 3D printing. And then we got to test and demonstrate the capabilities the shark had to offer.
For our system overview, starting with upper body subassembly, this contains the head and the electrical box. This electrical box contains the manifolds that are used to direct the air to actually control each individual piston. As far as the tail subassembly goes, we have the steering assembly. Steering pistons actually are going to guide the entire tail to actually vector the thrust. And then the propulsion pistons throughout the tail actually propel through the water back and forth repeatedly.
So a little bit about the design, calculation, and analysis of the tail. We wanted to emulate real shark's motion. So reading through literature, we were able to find that a lot of vertebrates experience about a 90-degree displacement from the nominal spine to the tip of their caudal fin, which is the tail fin of the shark. And the range of motion that we were looking for is about plus or minus 90.2 degrees. So here's a demonstration. It's going to be 3 videos showing the electrical assembly and then showing the tail in motion.
This is the electronic control subassembly that will go into the IP68 rated electronic box that will go into the upper body of the shark. Looking closer at the subassembly, first starts with the power supply that outputs 24 volts for the manifold and 5 volts for the Arduino. The Arduino is where the program for the shark is created, and it outputs a PWM signal. The signal then goes into an RC low-pass filter, which converts the PWM signal to a 0 to 5 volt analog signal. The terminal blocks connect to this DIN rail, connects the power, 24 volts wire, the ground, and the signal wires into the manifold. In the manifold, there are MPV pressure regulators from proportion air that controls the output pressure into the cylinders on the shark.
So let's get into some results. So you just saw the tail in action there, and how does it hold up against our designed tail? And we had about a 4.22%
error that we were able to measure by measuring the sedimented angles of each part of the tail subassembly. And yeah.
So for failure points, we had one issue in which the 3D printed clevis joints actually snapped during our testing. This was mainly due to the momentum the tail had going way too fast. It actually overshot and snapped it. The way to fix this is something 3D print on a strong material such as nylon, which we do have access to. Another issue is we have an air leakage issue on the actual hoses. We have all the fittings tightened down. However, we believe this is due to the improper hardware application for this actual task, and they are leaking a small amount and could be fixed if we just choose different hardware.
Thank you. Thank you.